Hello, and welcome to Lesson 25 of this Introduction to Differential Equations with Wolfram U. We have already discussed discontinuous functions and solving differential equations with discontinuous non-homogeneous terms using the Laplace transform. The discontinuous functions we encountered, like the unit step function, changed instantly from one constant to another constant at a particular point. In this lesson, we will consider impulse functions, which instead act only at a particular point and are zero elsewhere. We will need to introduce the very important Dirac-Delta function to describe impulse functions mathematically. Let's take a look at an overview of this lesson. There are many applications where you may want to describe a function that acts only over a very short period of time. Such would be the case where one taps a pendulum at rest to put it into motion. In this lesson, we will look at differential equations that have a non-homogeneous term that acts only at a particular instant or location. In order to model these situations mathematically, we will need to construct a special function known as the Dirac-Delta function. This function is modeled by the plot here, where the green line represents where the Dirac-Delta function is zero, while the blue dot represents the point where the Dirac-Delta is applied. To use these types of functions in differential equations, we'll need to first take a look at the Dirac-Delta function itself in a little more detail. To introduce the concept of a Dirac-Delta function, consider the function here. This function can be defined very easily in the Wolfram language using piecewise. This piecewise definition is saying that the function is equal to 1 over 2s when t is between minus s and positive s, while the function is equal to 0 when t is greater than or equal to s, and the function is also equal to 0 when t is less than or equal to minus s. It is important to observe what this function looks like for various values of s. This function is shaped like a rectangle, where the width of the rectangle is given by 2 times s, since the function is defined from minus s to s, while the height of the rectangle is given by 1 over 2 times s. Therefore, no matter what the length and width are for the rectangle defined by the function, the area of the rectangle will always be equal to 1. We can view the rectangle defined by this function for various values of s more easily with the manipulate function. The slider controls the value of s, which controls the width of the rectangle. The height of the rectangle is adjusted based on the function definition and the value of the width. The length is always equal to 2s, and the height is always defined to be 1 over 2s, so you'd expect the area highlighted in the plot to always remain constant at 1. It can be seen that we will arrive at the Dirac-Delta function when the width of the rectangle is 0. However, taking the width to 0 needs to be done with care, as a 0 width implies an infinite height, so we will need to take a look at the limit instead. As we have mentioned before, the box function we are constructing with the g function is designed so that the height gets smaller as the width gets larger, such that the area is always equal to 1. This result can be confirmed by integrating the g function over all values of t for a general value of s. The Dirac-Delta function can then be constructed by taking the limit as s goes to 0. Evaluating this limit in the Wolfram language gives the expected result for the Dirac-Delta function centered at the origin, where the function is 0 everywhere and only non-zero at t equals 0. We have been considering a model for the Dirac-Delta function consisting of a box with unit area and varying width. In the limit that the width of the box goes to 0, we found the definition of the Dirac-Delta here, where the Dirac-Delta function is indeterminate when the argument equals 0 and 0 elsewhere. Another tremendously important property of the Dirac-Delta function is that it is normalized. That is, the integral over all values of t is equal to 1. Using the definition of the Dirac-Delta in terms of a limit of the g function as the width of the box goes to 0, we can calculate the Laplace transform of the Dirac-Delta function. With knowledge of the Laplace transform of the Dirac-Delta function, we can solve differential equations with these types of impulse functions. Let's use our knowledge of the Dirac-Delta and the Laplace transform to solve the differential equation here. In this case, we are using initial conditions where the value of the solution at t equals 0 is equal to 0, while the first derivative at t equals 0 is also equal to 0. The Dirac-Delta function has an argument of t minus 1. Since the Dirac-Delta function is 0 everywhere except for when the argument is equal to 0, this represents a Dirac-Delta shifted 1 unit to the right. The Dirac-Delta function is represented by the plot here. The Dirac-Delta is applied at t equals 1, which is represented by the blue dot in the plot. The Dirac-Delta function is 0 everywhere else, which is represented by the green line. We can now define the differential equation in the Wolfram language, so we can proceed with finding the solution to this initial value problem. As we have done in many problems in recent lessons, we can solve this differential equation by first applying the Laplace transform to the entire equation. We see in the result that there are terms involving the solution at t equals 0 and the first derivative of the solution at t equals 0. Those two quantities are given as the initial conditions to this problem, so we can substitute in their respective values, which are both 0 in this case. After substituting in the initial values, we are left with an algebraic equation involving the Laplace transform of the solution, which can be solved. With the Laplace transform of the solution obtained, the solution to the initial value problem can be calculated by taking the inverse Laplace transform. We can visually see the effect of the forcing term on the solution in the plot here. It is seen that the forcing term has no effect until t equals 1 when it is applied. Since the initial value of the solution and its first derivative were both 0, the solution equals 0 up until the impulse is applied. Once the impulse is applied, it sets the solution into oscillatory motion. Since the delta function is 0 when t is not equal to 1 and there are no damping terms, the oscillatory motion will continue after the impulse is applied. This result can be verified with d-sol value. Plotting the result, we see that d-sol value and the result we found both agree. As a second example, let's solve the second-order non-homogeneous differential equation here, where the right-hand side is now composed of a sum of two delta functions. Notice that the magnitude of the first delta function is negative, so it would look like an upside-down box in our model of the delta function from earlier in this lesson. The two delta functions are shifted to the right, where the first one is applied at t equals 2 pi, while the second one is applied at t equals 3 pi. We can visualize the Dirac-Delta functions for this problem in the plot here. The two blue dots represent the two delta functions acting at t equals 2 pi and t equals 3 pi, while the two functions are 0 everywhere else as indicated by the green line. To solve this differential equation, we'll first need to define it in the Wolfram language. With the equation defined, apply the Laplace transform to the entire equation. The result includes a term with the value of the solution at t equals 0, and a second term involving the first derivative at t equals 0. These two terms can be replaced by their respective values since they are provided as the initial conditions for this problem. We now have an algebraic equation again that involves the Laplace transform of the solution to the initial value problem. The next step is to solve that equation for the Laplace transform. The Laplace transform of the solution to this initial value problem is given here. To get the solution to the initial value problem, take the inverse Laplace transform. Let's take a look at the solution to this differential equation and observe the effect of the impulse terms. Since the first impulse force was negative, the solution takes a negative trajectory after the first impulse is applied. The second impulse is positive. We can see that the slope of the solution just after the second impulse is applied is increased, which makes sense for a positive impulse when the slope of the solution is already positive. Let's calculate the solution with d-sol value. Plotting the solution from d-sol value, we can see that they are identical. Let's calculate the solution without the impulse terms. First, let's remind ourselves what the solution looks like with the impulse terms. Define the homogeneous equation, then solve the homogeneous equation with d-sol value. Plotting the result shows how the impulse terms affect the solution. Without the impulse terms, the solution has an oscillatory pattern with decaying amplitudes. Because the first impulse term was negative and the second impulse term was positive, the third peak in the non-homogeneous solution turns out to be higher than the second peak in the solution. This shows how an impulse term can modify the solution represented by the homogeneous equation. In this lesson, we introduced and constructed a new function called the DiracDelta function. Using the Laplace transform, we examined how forcing functions that appear as Dirac-delta functions influence solutions to differential equations. We looked at two examples. The first only had one impulse force, while the second example had two impulse forces. The plots on the left show the location of the impulse forces represented by the blue dots, while the plots on the right are the solutions to the differential equations we considered with these impulse forces. The location of the impulse force is evident in the shape of the solutions. We can also compare with the solutions of the homogeneous equation to see how the impulse forces affect how the solution would look without the impulse force applied.